This is Lab 3, Circuits, for Ben Skalka. Starting with the introduction and purpose, this lab involved predicting the behavior of circuits in parallel and in series. Additionally, we used multimeters to measure potential difference, current, and resistance. And lastly, the concepts of current conservation and the loop rule were used to obtain these values and to create equations that would allow us to find unknown variables. The series circuit model and experiment. Well, here you can see the circuit that we created, both the diagram and the actual in-person circuit that we created, as well as the resistance chart, helping us identify which resistance carried which ohm values. So both ammeters are in series, so they should read the same. Computationally and conceptually, we should get a result of 20.4 milliamps, as we can use Ohm's law and take voltage divided by overall resistance. And then you can see our experimental values. For the first ammeter, we got 18.5 milliamps, and the second one we got 18.4 milliamps. When the ammeter poles were reversed, the result is negative, so it would have just been negative 18.5 and negative 18.4. Continuing on, when one ammeter was swapped to measure voltage, we see that the ammeter reads 19.4 milliamps and the voltage measured was 1.925 volts. For potential difference along the 47 ohm resistor, we got 0.905 volts, and for overall circuit, we got 2.86 volts. And this makes sense because when we use Ohm's law again to calculate potential difference over the 47 ohm resistor, and we use it to calculate over the 100 ohm resistor, should add up to 3 volts. And when we get the potential across all components summed, we got 2.83 volts. So pretty close. Now moving on to the graph for potential difference, you can see how as the batteries are added, we get up to our value of 2.83 volts. And then as it goes along the two resistors, we see the drop down to 0. And essentially the potential difference will account for the voltage of the battery. And the loop rule will work out to the point where at the end of the circuit, it hits 0 volts. When the voltmeter is attached and we have an ammeter as well, it does change the circuit, but because the voltmeter has such high resistance, it draws negligible current, so it shouldn't affect the current reading of the ammeter, even when we are measuring voltage as well. Moving on to the RC circuit, we observed that with the battery, the bulb lighted up initially, and then it lost its brightness until it went out as the capacitance filled up. And then with just the capacitor and no battery, the bulb lighted up slightly, and then it also slowly died out. And here are our results. For the 10 ohm bulb, we got a charge time of 11.28. For the 20 ohm bulb, we got a charge time of 22.73, showing that when the resistance is doubled, we have essentially double the charge time, which matches up with the equations for capacitance in relationship to resistance and voltage. Moving on to what if? Well, if we charge the capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Well, ideally, the capacitor voltage should jump to V0 instantaneously. And if there's no resistance, hypothetically, then it should essentially be an instantaneous reach to full charge. But this doesn't really happen in real life because there is internal resistance in the circuit components, such as the wires and the capacitor itself and the bulb itself. So in practice, this doesn't actually work out because even with no resistor in the circuit, there still is resistance. So the ideal instantaneous jump to the highest voltage wouldn't actually happen. And so we don't really have an ideal circuit to represent this hypothetical scenario.